It is 6 p.m., but participants are yet to join. So we'll wait for a couple of more minutes before we get started. Good evening and welcome to week 6 of the live sessions for the course AE03 Computational Science and Engineering. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Shokte, who is from the Department of Aerospace Engineering at the Indian Institute of Technology, Kanpur. As usual, during the course of this session, we will first recapitulate some of the key concepts that were covered in the lectures for this week, and then we'll solve certain illustrative problems. And my hope is that it will help you to understand the topics better and to be able to more easily solve the questions that were posed in the assignment. And also, I hope that these sessions would help you in the final certification exam, should you have registered for it. And for seamless communication again, I request that rather than directly unmuting and speaking, you first raise your hand and I will call out your name. And then you might unmute and speak. And once we are done discussing, I request that you mute yourself again. This will ensure that communication in the session remains seamless. Now, starting this week, we have really come to the meat of the course, which is actual numerical techniques and numerical methods. And during the lectures, Professor Day discussed in great detail some machine arithmetic, a few methods such as Newton's method, false position, second method, and others. And also, he derived most of it and spoke about what possible pitfalls and what advantages each of these methods offer. One more thing which I would like to supplement to this course is how do we actually encode these methods into a program? Because in the end, uh, while knowing the science behind these methods is important, knowing how they're derived, how they work, and what is going on behind the black box. It is equally important to actually encode this or modulate it into a piece of code and run it for our practical needs. So for this session, we'll also try to devise some of the pseudocodes for say each of the numerical technique that we discuss. Now, why a pseudocode and why not a code? So when we discuss a method, we typically try to list down the steps in an unambiguous fashion and sequentially, of course. And our objective is that following the steps of an algorithm will lead us to the intended outcome. And a formal way to actually say describe this algorithm in a logical fashion would be a pseudocode. A code usually is, say bound rigidly by the semantics we use. So say the syntax we use might be different if you're using coding in a C++ environment versus say a Python environment or a Julia environment. So codes are often rigidly adapted and constrained by the environment in which you intend to run them. Whereas a pseudocode is simply uh, comprised of logical statements which are easy for us to understand. So they are human readable and they can be implemented in any code you like because they just describe the logic that we're supposed to implement. So we'll look at those, but first we'll start with machine numbers. And usually for real numbers, a 64-bit binary digit representation is used. The very first bit is a sign indicator denoted by S. So this one right here, and followed by an 11-bit exponent, C called the characteristic, which is here. So this denotes the sign, this is the characteristic. and the 52-bit binary fraction f called the mantissa, which is shown right here. And of course, for binary representation, the base of the exponent is 2. In decimal representation, it is 16. In hexadecimal, in decimal it is 10. In hexadecimal, 16. And we are free to actually express numbers in any base system we like. So it can be arbitrary like 5, 6, or 11. Usually, these are the most commonly used ones. Now, because of this way in which these binary machine numbers are designed, it is reasonable to assume that any real number represented in the system has at least 16 decimal digits of precision, which is very precise, but maybe not enough, as we'll see. And the exponent, which is made up of 11 binary digits, also gives us a range of 0 to 2 power 11 minus 1, which is the range of 2047 numbers. However, to ensure that we are able to adequately represent the negative numbers as well, uh, the exponent is actually ranging from minus 1023 to 1024. And here we have the floating point representation of the numbers. So it is, I'll just write it again, minus 1 power s, 2 power c minus 1023 times 1 plus f. Where the sign characteristic element is we already looked at. For example, here is a 64-bit number. The first bit, which is 0, if we remember correctly, this was S, and it actually refers to the sign of the number. So if S is 0, it means that the number is positive, and the next 11 bits actually correspond to the exponent. Sorry, the characteristic, which is called the exponent. So this one right here, this is C, and if we convert it to the decimal system, it will actually turn out to be 1027. The exponential number, which is this one, this being the mantissa, the exponential, which is 1027, is therefore to the power 4, and the final 52 bits give the mantissa, which again, when combined all together, the number which we're actually trying to represent is this one right here, 27.5664065. One thing to note, however, is that this representation is not, say, unique, or that we cannot represent every number of arbitrary precision using these binary digits. So we see here how that the next smallest machine number after this one right here is this, while the largest is this. And this, what this entails is that our original number does not only represent 27.5664065, but also half of the real numbers that are between this and the next smallest machine number, as well as half of the numbers between this and the next largest machine number. That is, our resolution is really limited to these discrete values between our exact machine number, the next smallest, and the next largest. We are not able to really resolve numbers in between. Thus, this binary code right here, this one, is actually a representation of any real number in this closed interval. So 27.5664062. Okay, these are really too many digits of precision. So this interval is closed and this interval is open. Our representation is not really unique, rather it is used for representing any number in this in a semi-open interval. Now, as we saw that the machine resolution is not does not hold till any arbitrary number of precise digits. Of course, we'll have underflow and overflow. And what these are, the smallest positive, normalized positive number that can be represented has sign 0, the characteristic 1, and the mantis is 0, and it is equivalent to 0.22251 into 10 power minus 307, which is pretty small, but no, maybe not small enough. The largest one which can be represented using this say convention is 0.17977 into 10 power 309. Now, any numbers which will be occurring in the intermediate calculation steps that have a magnitude, so sign is not really relevant here, we can deal with either negative or positive, but if they have a magnitude less than 2 power minus 1022, they cannot be resolved by the computer and they'll arbitrarily be set to 0, and this is called underflow. Similarly, any numbers which would be greater than 2 power 1023 times 2 minus 2 power minus 52 result in overflow. And what it physically means is that the number is simply too large for the computer to understand and work with. So unless we have special arrangements in place, uh, encountering any such number will simply lead to a stop of computation. Again, there are two representations for the number 0, which is really interesting. You would have thought it is unique, but there are two representations for the number 0. A positive 0 when S is 0, C is 0, and F is 0, and a negative 0 when the sign is changed to 1. The others remain the same. Now, during the lectures, we have seen how error may accumulate because of approximations. And the way to really approximate numbers is either by chopping or rounding them off. So, just for the sake of this discussion or for easier visualization, we work with machine numbers which are represented still in their normalized decimal floating point form. And they're usually called k-digit decimal machine numbers. And any positive real number within the numerical range of the machine, which we looked at, can actually be normalized to this form 0 point uh, many digits d1, d2 till dk plus 1, dk plus 2 into 10 power n. Now, this floating form of y, which is also denoted as float y, is obtained by terminating the mantis of y at k decimal places. And this termination or truncation can occur by two ways, as I said. One is called chopping, where we simply stop at dk digits. We do not care what came after. We only look at what was till the kth digit. And this will produce a floating point form of this kind. Originally, remember we had additional digits dk plus 1 and dk plus 2, but we simply chop them off without caring what they were. So dk plus 1 might have been even 9, and usually in rounding off, that would have implied that we increase the previous digit by 1. But when you're chopping, you do not really look at the subsequent digits. The other method, which is rounding, adds 5 into 10 power n minus k plus 1 to y, and then chops the result to obtain a number. Now, when rounding, if the next digit after the kth one, so digit k plus 1 is greater than or equal to 5, we add 1 to dk to obtain the floating form, that is, we round up. And when it is less than 5, we simply chop off all but the first k digit, so we round down. So equality is taken care of here. When we are rounding down, then all the digits till the kth one would be the same because we are not really caring what came after that. However, when rounding up, the digits and even the exponent might change. So let us just look at a quick example and practice how these and see how these chopping and rounding may affect our numerical values. So I've taken the simplest example of pi. Usually, so if I just use my calculator, pi till a few digits, only I know 3.141 Um, but just to be clear, let us see how many more digits there are. So it is 3.141592654. This is what any usual standard scientific calculator will give us. Now we have to determine the 5-digit chopping and rounding limits of pi. Now, if we are to say express it in our standard form, so we write floating pi for chopping. We simply have 5 digits, so 0.314115 into 10 power 1 because we took 3 after the decimal place. And that's it. We do not really care about rounding it off because they're chopping. So this would correspond to the chopping case. Then we are looking to round the values. Here we see that after 5, so 1, 2, 3, 4, 5, the sixth digit is actually 9, which is greater than or equal to 5. So we'll add 1 to the previous as we saw in this rule here. So in this case, the floating value representation of pi would be 0.3141. Okay, if I need to just break it down for us, 0.00001 because I'm rounding or chopping till the fifth into 10 power 1. It will simply be 0.31416 into 10 power 1. This is the rounded up value of pi. And we see that for this simple case, they might only differ in the fifth decimal digit to by a very small value. However, you can very well visualize that in a series of computations where these values are, say, where the intermediate values are chopped or rounded off at every intermediate step, you can very well see how the errors might accumulate and pile up. Again, another point that is important to define here before we move forward is convergence. Because whenever we are using any iterative method, an iterative method is one which, say, reaches the solution or reaches the root in a number of steps rather than in a single step. And it might also use the values obtained in a previous step to compute values for the current step. Now, we want it to converge, else the process can go on forever without an end. And to check whether it can actually converge to a value or not, we have to define a check for convergence. So here is a formal definition. Let's suppose the sequence of Pn from n equals 0 to infinity is sequence that converges to P with Pn not equal to P for all n. So it is not trivially true. If positive constants alpha, lambda and alpha exist with limit n tending to infinity, the absolute value of Pn plus 1 minus P by the absolute value of Pn minus P raised to the power alpha is lambda, then the sequence Pn where n goes from 0 to infinity converges to P of order alpha with asymptotic error constant lambda. And any iterative technique of the form Pn is g of P of n minus 1. So the value obtained in the nth step is actually some function of the value which was obtained in the previous step, is said to be of order alpha if the sequence converges to solution P equals g of P of order alpha. And in general, any sequence with a high order of convergence converges more rapidly than a sequence with a lower order. Say, for instance, a method which has quadratic convergence will actually converge more quickly than a method which only has a linear convergence. The asymptotic constant affects the speed of convergence, but not to the extent of order. So, order is a greater deciding factor. If the order alpha is equal to 1 and the lambda is less than 1, then the sequence is linearly convergent, like say for the case of bisection. If alpha equals 2, the sequence is quadratically convergent, which is usually true for Newton's method, where we're dealing with only a single root. If there are multiple roots, we might even see that, say, Newton's method converges quadratically in some of the cases, but in some, but in the determination of some other roots, it will converge, but it need not converge in a quadratic fashion. Another quick example. So errors were discussed in class. So let us have a simple exercise and try to determine the absolute and relative errors. And perhaps more importantly, have a feel of which error metric should be report or use for our computations. So just uh, before getting started, let's define what the error is. I'm sure everyone remembers, but still, just for the sake of it. So if our exact value is p and the approximation, so here it's denoted by p star, then the true error or the absolute error is the absolute value or difference of p minus p star, and the relative error is absolute value of p minus p star by absolute value of p. And this is easy to remember because just by the use of the term absolute, we know that this error cannot be negative. We're talking about the absolute value of the error here. So let's start with case A, where p is 0.3000 into 10 power 1 and p star is 0.3100 into 10 power 1. So our absolute error in this case would be absolute difference of p minus p star, which shall equal 0.0100 into 10 power 1 equals 0.1, and our relative error in this case will be absolute difference of p minus p star by absolute value of p, 0.1 by 3, and this comes out to 0.0333 recurring, or to put it in a consistent notation, this will be 0.333. We are using the 4 digits after decimal into 10 power minus 1. Alright, that is it for the first case. Let's look at the second one, where p is again 0.3000 into 10 power minus 3. Okay, so the exponent is different this time, and the approximation is 0.3100, 10 power minus 3. Now again, the absolute error will equal to the absolute difference between p and p star, which is equal to 0.0100 into 10 power minus 3, 0.0001. Or for consistent notation, 0.1 into 10 power minus 4. I think there is one additional zero here, sorry. Yes. And the relative error, 0.1 into 10 power minus by 0.3000 into 10 power minus 3, which equals zero point 0.1 by 0.3 into 10 or zero point 0.1 by 3, which shall equal 0.0333 recurring, or in our conditional notation 333 recurring into 10 power minus 1. Similarly, for the third case is 0.3 into 10 power 4. The approximation P star is 0.3100 into 10 power 4. The absolute error is absolute value of P minus P star, which is equal to 0.0100 into 10 power 4, or 0.100 into 10 power 3. The relative error is 0.100 into 10 power 3 by 0.3000 into 10 power 4, or once more it is zero point 0.1 by 3, or 0.3333 into 10 power minus 1. And perhaps the interesting thing to note here is that every time the relative error was the same, whereas the absolute error is differed by several orders of magnitude. Here you have of order, say, 10 power minus 5, there is of order 100, and here of order zero point 0.1. Yet in each case, the relative error was the same. Thus, often in situations of scientific and technical discussion, we'll find that it is not really the absolute error which matters, because the quantities or magnitudes we are working with again are say of a similar order or similar scale to the error. Rather, it is a relative error which will matter most, because even if I'm working with very large, even if I have a very large absolute error, but the quantities I'm working with are also numerically very large, the percentage error will still be small. Whereas even if I have a very small numerical absolute error, but the quantities I'm working with are highly precise, or they are, say, very small. In such cases, the relative error is indeed very large. So usually we'll find that it's better practice to report the relative error rather than the absolute error. Now we'll look at some of the basic theorems of calculus. Uh, all of these theorems are known to us, but it's important to go over them again, because these theorems actually form the background of some of the processes that we will be discussing, especially the intermediate value theorem, which is actually what guarantees that we'll find a solution in bisection. So starting with the Rolle's theorem. So suppose f is continuous, this symbol means continuous, on the closed interval a comma b, and f is differentiable on the open interval a comma b. If the value of the functions at a and b are the same, then there exists a number c in the open interval ab with the derivative of the function at that point equal to 0. And here we also have a illustrative figure. Next is the mean value theorem, which says that if f is continuous on a closed interval ab and again differentiable on the open interval ab, then there exists a number c in the open interval ab such that f prime of c is equal to the mean, in a way, the mean slope. So fb minus fa by b minus a. And the way it is illustrated here is that there will exist at least one point, C, at which the slope will actually be equal to or parallel to the line we get when we are actually joining the value of the function with two endpoints. And the slope we get by, say, subtracting the value of the function at these points, dividing by the uh, ordinate distance between them, the abscissor distance between them. If we have a mean value theorem, of course, we'll have an extreme value theorem, which says that if a function is continuous on closed AB, then there exist 2 points, C1 and C2, in closed AB with f of C1, or the functional value at C1, less than equal to the functional value at x, less than equal to the functional value at C2, for all such x which belong to the closed interval AB. And additionally, if f is also differentiable on the open interval AB, then the numbers C1 and C2 occur either at the endpoints or where f prime is 0. And very clearly, this is where the idea of differentiating or taking the derivative of a function, putting it to 0 for finding the minimum or maximum arises from. It's actually from the extreme value theorem. And this is actually the intermediate value theorem. So yeah, I forgot to change the header. Now, if f is a function which is continuous on closed AB, and k is any number between uh, functional value of A and functional value of B, then there exists a number C in AB for which f of C is equal to k. Now, this might appear very elementary or even intuitive, but where the power of this theorem really emerges is when k is equal to 0. So when you have a case where for your coordinate system, the function is varying such that it passes through the x-axis, or when k is equal to 0. Then we see that this theorem may very well be exploited to actually find the roots of such a polynomial. The last and perhaps one of the most important is Taylor's theorem, which we'll keep encountering again and again in the duration of, say, this course or any other course of a similar nature. And what it says is that suppose the function f is nth order continuous on the closed interval AB, such that the n plus 1th derivative of f exists on closed AB, and x naught belongs to closed AB as well. Now, for every x belonging to closed AB, there exists a number zeta of x between x naught and x, with fx equals some Pn of x plus some remainder term Rn of x, where Pn is actually the polynomial found by the series, which is formed by the summation f of x naught plus f prime of x naught and x minus x naught plus f double prime x naught by 2 factorial x minus x naught square. So the usual form of the Taylor series expansion till the nth term, which is nth derivative of f at x naught by n factorial times x minus x naught power n, which is of course case more elegantly represented by this sum. And you have the remainder term, which is the n plus 1th derivative of f evaluated at zeta x by n plus 1 factorial times x minus x naught power n plus 1. Now, the first method we'll be looking at is the bisection method. And suppose f is a continuous function which is defined on the closed interval AB, and fa and fb have opposite sign. Now, this is very important And what it really means is that you have any arbitrary function and you are looking at 2 points within the interval in which this function is defined. And say one point is here, the other point is here. Then we check whether the signs of the function at the 2 points are the same. Here we see that uh, they are the same. So if f of a, this f of b, then signs in both cases are positive. So we can never really be sure, given the information of just these 2 points, whether the function ever actually crossed the x-axis or not. That is, whether the value of the function was ever zero or not. Because between these 2 points, they may have varied by any way. Also have been a straight line, or it could even have passed the x-axis multiple times. But if we are given a situation where we have an interval where the function takes on different signs, then we can be pretty sure that the function or the plot of the function did cross the x-axis at least once. It could have been more times, but what we can be sure is that at least once the value of the function, the plot of the function did cross the axis because it's a continuous function. Its values are varying continuously. So it cannot simply arbitrarily jump from a positive to a negative value or vice versa. It has to pass through zero. And this is the basic idea behind the method. So if f is continuous, defined on interval closed AB with f and fb of opposite sign, the intermediate value theorem, which we just looked at some time ago, implies that there exists a number p in closed AB with f of p equals 0. So we set the value k equals 0 here. And it will still work when there is more than one root. We assume for simplicity that the root in this interval is unique. So just because we are getting introduced to the method. And in this method, what we'll do is we'll repeatedly halve or bisect the subintervals to find the interval which contains the root p. And ultimately, by this halving the interval each time, we'll try to ultimately arrive at the root itself. And here we have say some semblance of the method, not quite a pseudocode. So we set a1 equals a and b1 equals b, and let p1 be simply the midpoint of a and b. That is, the first part or our first guess of the root is a1 plus b1 by 2. Now, if p1 is equal to 0, then we are done. If the value of the function at p1 is 0, then we are done, because that will imply that p1 is a root of the function. But if it is not 0, which will usually be the case, because if it was so easy to find a root in the very first step itself, we would not have resorted to such numerical techniques. Then either the value of the function at p1, so say if p1 comes out to be here, then the value of the function at p1 is again positive, so it is the same as f of a. Then what we'll do is we'll set a equals to p1 so that at least the discrepancy in signs is maintained. At least, I mean, both have opposite signs, because that is how we are sure of bracketing the rule. It only be contained in an interval at the endpoints of which the function has opposite signs. So if p1 has the same function of p1 has the same sign of a, so best to write it as, so here the value is f of p1 and the corresponding point here is p1. If f of p1 has the same sign as a, we set a equals p1 for our next iteration. If p, f of p has the same sign as b, we set b equals p for our next iteration. And thus we can see that originally we started with, say, this interval. After one step, though it's not exactly at the midpoint, but still. Iteration. This is the first iteration. Our interval or the window which we're. Now, the bisection method, though conceptually very simple and clear, has some drawbacks. It is slow to converge, and we may have to perform this bisection and search step a large number of times. And a good intermediate approximation might be advertently discarded in certain cases. However, where the most powerful aspect of this method is that it will always converge to a solution, which cannot really be said for all the methods we'll be encountering. And here is a graphical depiction of the method. So we see that how for the function y equals fx. In this case, we assume that it only has one unique root occurring at p. We start with the intervals a and b. So for our first step, a equals a1, b equals b1, and then intermediate point is p1. Now we see that p1 lies in the upper half plane, and thus the value of the function at p1 sorry, P1, the value of the function at P1 lies in the upper half plane, and it has the same sign as the value of the function at B1. So we substitute B1 equals P1 as seen here. So B2 is equal to P1 in this case. A1 remains the same as A2. And then we find its midpoint, P2. And we see that the value of the function at P2 now is negative. So it is same as the value of the function at A1. So now we'll have to change A1. And so P2 becomes A3, whereas the other uh, end of the interval, which is B2, remains the same. And then we obtain the third point, B3, which is here. Again, we see that the value of the function at P3 is negative, so P2 will change. So the next step may be seen as something like this. We have A4, which is in fact equal to P3, and we have B4, which is still equal to B3 unchanged, and we find its midpoint, which will be some P4. And now you'll find that maybe P4 will have a very good approximation to our original root P. And thus, within, say, a good enough tolerance or a user-defined small tolerance, uh, the method will approximate the root within 4 steps only. Again, we have a further example to look at. So we have a function, a polynomial really, which is x cubed plus 4x squared minus 10 equal to 0. We are supposed to show that it has a root in the closed interval 1, 2, and use the bisection method to determine an approximation to the root that is accurate to at least within 10 power minus 4. How do we show that it has a root? Maybe the intermediate value theorem will help. So let's just calculate the value of the functions at the two ends of the interval. So the value of the function at 1 is 1 cube plus 4 times 1 square minus 10 is equal to 1 plus 4 minus 10 is minus 5. Value of the function at the other end is 2 cube plus 4 times 2 square minus 10, 8 plus 16 minus 10, which is 14. So we see that the signs of the function values of the two ends are different. Therefore, since f of minus 1 dot f of 2 is less than 0, which basically means that their signs are different, the intermediate value theorem guarantees. the existence of a root. At least one root, so to say, in the closed interval 1 comma 2. The first part was pretty straightforward, but now we also have to find it. So let's perform a couple of iterations of the bisection method. So say for the first iteration itself, we have a1 equals a, which is 1, b1 equals b, which is 2. So p1 will simply be a1 plus b1 by 2, which is equal to 1 plus 2 by 2, so 1.5. We also compute the value of the function at this. So this is 1.5 cube plus 4 times 5 square minus 10. I'll just use a calculator for this. 1.5 cube plus 4 times 1.5 square minus 10, which is 2.375 greater than 0. Since it is greater than 0, for my next iteration, I'll just start here. The value of the function at 2 was also greater than 0, so b will change. So a2 remains the same as a1, whereas now b2 takes the becomes equal to p1, equal to 1.5, and we calculate p2 equal to a2 plus b2 by 2, which is 1.25 if I'm not wrong. Sorry, I'm just looking at the midpoint of 1 and 1.5. And we again calculate on the value of the function at p2. I'll just use the calculator directly. So this will be 1.25 cube plus 4 into 1.25 square minus 10, which comes out to be negative 1.7969. Thus, for my third iteration, this is the value of the function at p2 is negative. The value of the function at a2 is also negative. So I'll change a2. I will change the a interval. So a3 will actually become equal to p2, which is equal to 1.25, whereas my b remains unchanged. So b3 is same as b2, which is equal to 1.5. The midpoint now is a3 plus b3 by 2, which is between 1.25 and 1.5. 1.375 is it? 1.25, 1.375. And let us also calculate the value of the function at this point. 1.375 cube plus 4 into 1.375 square minus 10 is positive 0.1621. Since it is positive, we'll change the b n now. So a4 is same as a3, which is 1.25. b4 will actually equal p3, which is 1.375. And you will see how in each step we are simply bracketing the root, or we are moving, trying to contain it within 2 points. Now for this p4 or the midpoint, will equal A4 plus B4 by 2, 1.25 plus 1.375 by 2, which is equal to 1.3125. The value of the function at this point, to 1.3125 cube plus 4 times 1.3125 square minus 10, which is negative, minus 0.8484. And if we are to continue doing these iterative steps, hopefully with a computer, we'll find that, say, after the, I have done this somewhere, after the 13th iteration, we will have the root within, this will be equal to 1.365112305. So many more significant digits than I have been showing here. And this root will be within an error, the 1000122070. And this will ultimately be our uh, root. Okay, maybe one step further because we want to have it within 10 power minus 4. So one more step and you'll find your root. So we see that even though it was guaranteed that the method converges and the method was reasonably simple, it took us at least 14 steps of continued iterative calculations to arrive at the root. So maybe not the fastest, even though it is very uh, stable. Oh, I also have a table here. So till the 13th root, I have shown the calculations, and in the 14th step, we get our root. And yeah, the most important thing is to write a pseudo code for this. So let us get started. When you are writing the pseudo code, we should know the objective, which is clear. So we have to find a solution. Fx equals 0. So given the fx is continuous on the closed interval AB, and of course, fa and fb have opposite signs. Let's look at the inputs. Inputs would, of course, be the endpoints A and B, the tolerance within which we want our error, say, just using the variable t while for this, and of course, the maximum number of iterations that we want. So, because we don't want this process to continue indefinitely, or sometimes what may happen is that due to some error in the code, the program simply does not terminate and continues going on in an endless loop, which is something we want to avoid. So we also specify the maximum number of iterations. The output we desire is either the approximate solution within the tolerance limit, or if nothing else, at least a message of failure. Because we should know that something is wrong with the code. It should not just terminate by itself and leave us in the dark. And the way to do it will be, so in the first step, we start by counting our iteration. So we set the counter to 1 and set the functional value at a denoted by some variable, say fa equals f of. Now step 2, While this iteration is less than equal to the maximum number of iterations, we perform steps 3 to 6. Step 3 is to find the midpoint, which is p equals a plus b by 2, and also find the value of the function at p. So fp is equal to f at p. The next step is if this value is equal to 0, or if our interval is less than the tolerance, we don't want to keep resolving it unnecessarily, then we output p, because if of p equal to 0, then this is our root, or we have resolved it to our tolerance and do not want to continue further, so we have the approximate root, and thus we stop. Very importantly, if not, we increase the counter. So it did not get solved in this iteration step. Now if fa dot fp greater than 0, that is the sign is the same, then p will become a. Similarly, fa will become fp, and if this is not the case, the signs are opposite, then b will become p. And this will continue till the maximum number of steps are consumed. And if it is not solved and we do not get a root output, it means that our method has failed. So we should have an output. It can be something as simple as method failed after n not iterations, where we can also show where n not was what, even though it is already a user input or maybe hard coded as the way it was, and then we put a stop message again. So this is a pseudocode which can be implemented into any particular code programming language. There's also a way to look at or at least gauge the number of iterations which the bisection method will take. So the bisection actually generates a sequence where each of p such that after n iterations, the absolute value of pn minus p will be less than equal to p minus a by 2 power n, where n is greater than equal to 1. And I also have an illustrative example here where we can like guess the number of iterations necessary to solve fx. So the same polynomial we looked at before with accuracy 10 power minus 3 using a1 equals 1 and b1 equals 2. So the same guesses. So the way to do this is to use logarithms. You already know that pn minus p is equal to b minus a by 2 power n. But the RHS can also be written as b minus a 2 power minus n. And this has to be less than 10 power minus 3 because this is the accuracy we're looking for. And if you just use base 10 logarithms, so 2 power minus n is, here we already have, so 2 minus 1 power 2 power minus n less than 10 power minus 3 implies 2 power minus n less than 10 power minus 3, which implies that we take logarithm of both sides using base 10. 2 power minus n less than logarithm base 10, 10 power minus 3, which implies that minus n log base 10 of 2 less than minus 3 log base 10 of 10, which is simply 1. Minus n log base 10 of 2 is less than minus 3. If I run out of space, I'll just continue on the right hand side here. Or since we are multiplying both sides by negative sign, the inequality will flip. N log 2 log base 10 of 2 is greater than 3, which implies that n is greater than 3 by log base 10 of 2, or n is greater than, let's compute this, 3 divided by log 2, 9.9658. Therefore, n is equal to 10. The bound which you get in this case is 10 iterative steps, but we also have the value tables here. So let's see. Here we can see that in the ninth iterative step itself, we achieve the root within tolerance of 10 power minus 3, whereas this theorem predicts 10 steps. So it's a conservative value really rather than the exact value. And this is more of an upper ceiling. So it guarantees that within 10 steps, we will arrive at the solution. So yeah, this theorem can prove pretty useful in case you're looking to actually gauge how many number of iterations we'll need. So before we move on to Newton-Raphson, we'll just take a short break here. We'll resume in say 10 minutes. So let us resume. We'll next look at the Newton-Raphson method, also just simply called Newton's method in some texts. And the way it is formally stated is that suppose that f is continuous till the second derivative on the closed interval a comma b, and let p not belong to a comma b and be an approximation to p, so that f prime of p naught is not equal to 0 and p minus p naught is small. How small it is really an arbitrary definition. Often it might even be asked as user input, or you'll have to be hard coded to you. And we go back to our Taylor polynomial, and when we expand fx using the Taylor series about the point p naught and evaluate it at x equals p, the formulation will be something like this: f of p equals f of p naught plus p minus p naught f prime p naught by 1 factorial plus p minus p naught square by 2 factorial f double prime of zeta p. Here zeta p lies between p and p naught. Now since f of p is equal to 0 as per our definition, this equation will give 0 equals f of p naught plus p minus p naught f prime of p naught plus p minus p naught square by 2 f double prime of zeta of p. And since this absolute difference of p minus p naught is small, the term involving p minus p naught square will of course be negligibly small. And thus we can actually approximate it to the first order term itself. So f of p naught plus p minus p naught f prime of p naught will equal 0. And should we solve for p, it will yield p equals p naught minus f of p naught by f prime of p naught, which can then act as our value of the root for the next iteration. And if we continue to perform this iteratively, so p2 will equal p1 minus f of p1 by f prime of p1, p3 will equal p2 minus f of p2 by f prime of p2, and so on. This sets the stage for Newton's method, which starts with an initial approximation p0 and generates the sequence Pn, where n goes from 0 to infinity, by Pn equals Pn minus 1 minus f of P1 by f prime of Pn minus 1 for all n greater than or equal to 1. Now, Newton's method is extremely powerful, and it also will usually converge quadratically. However, it has the major drawback, which is the need to know the value of the derivative f at each approximation. So in addition to computing the value of the function itself, we're also computing the derivative, and often the calculation of this derivative will be far more difficult and far more computationally intensive than calculating the value of the function itself. Here we also have a graphical representation of the method, and if we are to say formalize the method into a pseudocode which can be implemented, let us write one. So the objective in this case is to find a solution to fx equal to 0 given an initial approximation p naught. Again, based on how good or how close enough this approximation is, our convergence will be fast or slow. Thus, giving a reasonably good approximation or initial guess is highly important. Often, when we implement this in a code, we seek the guess from the user only as user input. In this case, the inputs will have the initial approximation P naught often as a user input. I have the tolerance, again just denoted by this generic tol variable, and the maximum number of iterations. In this case, n naught. And the output which we desire is the approximate solution to the function, or as we discussed, Our program should not run indefinitely. So if something is wrong, we should know about it. Thus, a message of failure. And the algorithm, of course, this is not unique. Whatever I'm writing or discussing is, say, one possible way to encode this. There might be other equally valid or even more efficient ways. So one way to do it would be that in the first step, we will start with our iteration counter. Then we place a condition on the iteration. So while the number of iterations is less than the maximum number of iterations allowable, we perform the following steps. Step 3 can be, so we set p equals p naught minus f at p naught by f prime at p naught. We check if this is good enough. That is, if the absolute difference between this new guess and our original guess, if it's smaller than the tolerance defined to us, then we stop the program and output this as our solution. And of course, stop. If not, we continue. We consumed one iteration, so we'll have to. We are going into the second iteration now, and we also update the value of p naught. That is for the next step. Our previous p now becomes our p naught. As we saw, pn is equal to pn minus 1 minus f of pn minus 1 by f prime of pn minus 1. In the next step, if this does not say converge within the given number of maximum iteration, then we'll assume that the program has failed, and thus we must output a failure message. Say the method failed after maximum iterations, and not equals whatever that number of iterations was. And again, we must remember to stop. We also do a few iterative steps of this manually. So say we have the function fx equals cos x minus x equal to 0, and we are asked to approximate a root of this function using Newton's method. It is also graphed here for our convenience, and we see that the solution of y equals x and y equals cos x occurs somewhere here, except we don't quite know what that point is. So let us perform a few. So this, I think it will be reasonable to assume as our initial guess p naught equals pi by 4, since this point looks to be around, say, halfway between 0 and pi by 2. And it's best if we also compute the function derivative of the function cos x minus x. So f prime is minus sin x minus 1. So let us perform the first iteration. P1 is p naught minus f of p naught by f prime of p naught, which is equal to pi by 4 minus cos pi by 4 minus pi by 4 pi minus sin pi by 4 minus 1. Just use the calculator for this. Cos of pi by 4 minus pi by 4 divided by minus sine of pi by 4 minus 1 and pi by 4 as this answer equal to 0.7395. By the way, pi by 4 itself is 0.785398. Okay, so this value is radically different from P naught, I don't think, even for any given tolerance. We are close enough. So we should perform a second iterative step. In this case, P2 will equal P1 minus f of P1 by f prime of P1. So P2 is equal to 0.7395 minus cos of 0.7395 radians minus 0.7395 by minus sine of 0.7395 radians minus 1, which shall then equal 0.395 minus 0.7395 divided by minus sine 0.7395 minus 1, 0.395 minus answer. This comes out to be 0.739085. Okay, I'm sorry, I did not maintain consistency in the number of digits. This one was 1395, 36, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 6. Okay. Again, let's perform a few more iterations. P3 will be P2 minus f of P2 by f prime at P2, which should equal 0.739085 minus cos 1739085 minus 0.739085 by minus sine of 0.739085 minus 1. I just use a calculator for this. So cosine of 0.739085 0.739085 divided by minus sine of 0.39085 minus 1 0.739085 as this entire thing is 0.739085 again. We just add a few more digits. So this was 1781. This is 1332. So we are close enough, but just for the sake of it, let us perform one more iteration. This will help us clear concepts. So P4 will be P3 minus f of P3 by f prime of P3. 0.739085 1332 minus cosine of 0.7390851332 0.7390851332 by minus sign of 0.7390851332 minus 1 739085133 minus 17390851332 divided by negative sign of 739085133 minus 1 7390. We see that this quantity on the right here, 739085133 is actually of the order of 10 power minus 11, which is really small and within given tolerance in most cases. So we'll just stop here at 51332. Cancel this is 739085133 itself. And thus we stop here. Or we say that the method has converged. And this is a reasonably good approximation to the root. We saw how the Newton's method or the Newton-Raphson method had the computational effort, involved the computational effort of calculating the derivative at every step. To override that or to sidestep it, we introduce a slight variation in the second method. Now, by definition, the derivative is simply at any point Pn minus 1, this is the limit x tends to Pn minus 1, fx minus f of Pn minus 1 by x minus Pn minus 1. And say after a reasonably large number of steps, the values Pn minus 2 and Pn minus 1 will be close together. And this can further be simplified as Pn minus 2, f prime at Pn minus 1 is f of Pn minus 2 minus f of Pn minus 1 by Pn minus 2 minus Pn minus 1. And when we apply this approximation to the Newton's formula, rather than the derivative, we simply have to compute the value of the function at 2 points. So Pn now becomes Pn minus 1 minus f at Pn minus 1, Pn minus 1 minus Pn minus 2 by f of Pn minus 1 minus f of Pn minus 2. Thus here we start with two initial approximations, P0 and P1, and it might be seen that the approximation P2 is the x-intercept of the line joining these 2 points. So we have P0 and f at P0, we have P1 and f at P1, and when we draw the straight line joining these 2 points, it intersects the x-axis at the point P2. Now we repeat this. So this is f of P2, this is still f of P1, and when we draw the straight line joining these 2 points, we end up with point P3. And when we join so on, it will continue. And only one function evaluation is needed per step for the second method after P2 has been determined. Whereas in contrast, each step of Newton's method requires an evaluation of both the function and its derivative. The convergence of the second method, while faster than a few iterative methods, is slower than Newton's because Newton's has usually quadratic convergence. And the way to usually implement these methods is that either Newton or the second method will simply be used to refine an answer which is already obtained by a simpler or more rigorous technique such as, say, the bisection method. And the reason for that is because, as we discussed, the initial guess or how good the initial guess is will often determine how long it takes for the method to converge. So we need a reasonably good initial guess. We get that guess from a method such as bisection, and once we have a guess, we implement either, say, the second method or Newton's method to reach the solution quickly. So these methods require good first approximation, but give rapid convergence. So similar to the case for Newton, we'll also let's also try to devise a pseudocode for the second method. And again, in this case, our goal is the same as Newton's. We have to find a solution to fx equal to 0. However, in this case, we need two initial approximations, being p0 and p1. So the inputs in this case would be the initial approximations p0 and p1, the tolerance, and the maximum number of iterations. The output is an approximate solution. Of course, notice how I'm never saying the exact solution because while the exact solution might indeed be reached within the, say, the defined number of maximum iterative steps, it cannot be generally said that we'll always end up reaching the actual exact solution. So it's best to assume that what we'll reach is, say, a very good or a close enough approximation rather than the exact solution. However, the exact solution may indeed be reached for some simple cases. Or in case we're not able to reach the solution, we need to know that something is wrong. So message of failure. And what can be the steps? Here we start by already setting the iterative count to 2 because we are computing these two values. Say rather than P, we denote them by Q here. And then when these are the function values, then we start our iterative steps. So while the number of iterations is less than equal to the maximum per method, we do the upcoming steps. Now this is simply, say, right, this statement right here, P equals P1 minus Q1 times P1 minus P0 by Q1 minus Q0. If this P that we obtained is small enough, and the difference between this P and any P from previous step is small enough, smaller than our prescribed tolerance, then we have reached our solution. We will output this P as well as we'll stop any further computations. If not, we increase the counter and we update the values of our variables. Q naught equals Q1, P1 equals P, and Q1 equals F at P. And these steps will continue. However, even after reaching the maximum number of iterations, if we are not successful, then we must output a failure message. And this step 7 will only be reached if we do not already exit within the step 4 right here. That is, if the solution is not reached within the number of iterations. So we'll output the method failed after maximum number of iterations. And we can also display this number. And of course, you must remember to stop. Now, the cases we discussed thus far were for a single unique root within the given interval, and that was assumed for the sake of, say, simplicity and easier understanding. However, that does not really mean that the methods themselves are limited to cases where only one root or one unique root may be present in the prescribed interval. In fact, there are ways to deal with multiple roots. Also, another restriction was that f prime of p not equal to 0 because we were dividing by it, where p is a solution to fx equals to 0. And in particular, Newton's method and the second method will generally give problems if f prime of p equals 0 and f of p is 0. And the way to deal with this, first of the definitions. So any solution p of fx equal to 0 is said to be a 0 of multiplicity m of f. If for x not equal to p, we can write f of x is equal to x minus p power m q of x, where limit x tends to p, q of x is not equal to 0. And what this actually means is that qx represents the portion of fx that does not contribute to the zero of f. And the way to easily identify simple zeros, or simple zeros are ones which have the multiplicity of 1. Now, any function f which is, say, continuous of order n in the closed interval AB has a 0 of multiplicity m at p in open AB if and only if 0 is equal to fp is equal to f prime of p equals f double prime of p, and so on till the m minus 1th derivative of f evaluated at p, but the mth derivative of f evaluated at p is not equal to 0. This indicates that an interval about p exists where the Newton's method converges quadratically to p for any initial approximation p not equals to p, provided p is a simple zero. And how Newton's method is modified to deal with multiple zeros is shown here. So we define this quantity mu of x equals fx by f prime of x. If p is a zero of f of multiplicity n with fx equals x minus p power m qx, as we just saw a little while ago, then as per this definition, mu x will turn out to be x minus p times qx by mqx plus x minus p q prime x, which will again have a 0 at p. However, q of p itself is not equal to 0. So qp by mqp plus p minus p, so this term goes to 0. And only 1 minus m will survive, which is not equal to 0. And p is a simple 0, mu x. And Newton's method can thus be applied to this modified quantity mu x as gx equals x minus mu x by mu prime of x is equal to x minus fx f prime x by f prime x square minus fx f double prime x. So this modified Newton's method can very well prove useful in dealing with cases where you have multiple roots. Again, another problem with applying the regular false or false position analysis method to polynomials is the possibility that the polynomial may have complex roots, even when all the coefficients are real numbers. However, till now, whatever computation we performed, we took the initial guesses as real numbers, and whatever operations we performed ensured that we'll only obtain real numbers only. But what if the roots of the polynomial we're dealing with, at least one of the roots, at least one pair of roots is complex? What do we do in such a case? So if the initial approximation is a real number, all subsequent approximations will also be real numbers, which is what we have been doing this far. And one way to overcome this difficulty is actually to begin with a complex initial approximation and do all the computations using complex arithmetic, so maybe a brute force way. An alternative approach is based on the following theorem. So if z equals a plus b is a complex zero of multiplicity m of the polynomial px with real coefficients, then its conjugate z bar is a minus bi also has a zero of multiplicity, is also a zero of multiplicity m of the polynomial px, and additionally x square minus 2ax plus a square plus b square whole power n is a factor of p power x. And a method which actually implements this is Mueller's method, which is illustrated here. So we recollect how the second method actually begins with two initial approximations p0 and p1 and determines the next approximation p2 at the intersection of the x-axis of the line through p0 fp0 and p1 fp1. Now Mueller's method instead starts with three initial approximations p0, p1 and p2 and determines the next approximation p3 by considering the intersection of the x-axis with a parabola through the points p0 fp0, p1 fp1 and p1 fp2, p2 fp2 as seen here. So previously we saw how if this is p0 and this is fp0, p1 and fp1, we join these two, and wherever this intersects the x-axis is where our next point lies. For Mueller's method, we have three initial approximations, p0, p1 and p2. We fit a parabola through the points p0 fp0, p1 fp1 and p2 fp2. Wherever this parabola intersects with the x-axis is where we assume our next point, that is p3 to lay. Further, let us define these quantities a, b, and c, where c is f of p2, b is p0 minus p2 square times f of p1 minus f of p2 minus p1 minus p2 square times f of p0 minus f of p2 whole divided by p0 minus p2, p1 minus p2, p0 minus p1. So pairwise differences. And the quantity A is defined as P1 minus P2 times f of P0 minus f of P2 minus P0 minus P2 times f of P1 minus f of P2 whole divided by again the product of pairwise differences P0 minus P2, P1 minus P2 and P0 minus P1. And to determine P3, 0 of P, we apply the quadratic formula to Px equal to 0. However, like we discussed, round of error problems caused by subtraction of nearly equal numbers, we apply the formula in a manner prescribed in some of the section of the textbook, where P3 minus P2 is actually taken equal to minus 2c by b plus minus under root p square minus 4ac. And this formula then gives two possibilities for P3 depending on the sign preceding the radical term. So we have a plus minus sign here. In Mueller's method, the sign is chosen to agree with the sign of b. So this is, say, a convention or a manual choice. It is not, say, unambiguously implied by the method in some fashion. The sign is chosen to agree with the sign of b, and when chosen in this manner, the denominator will be the largest in magnitude and will result in P3 being selected as the closest zero of P to P2. Thus, P3 equals P2 minus 2C by B plus sine of B under root B square minus 4AC. So SGN is generally the signum function and generally gives the sine of B. Now, once P3 is determined, the procedure is reinitialized using P1, P2, and P3 in place of P0, P1, and P2 to determine the next approximation P4 and continue in an iterative fashion. This method continues until a satisfactory conclusion is obtained. Now, at each step, the method involves the radical b under root of b square minus 4ac, and so the method gives approximate complex roots when b square minus 4ac is less than 0. So that is all I had to discuss for this week. The session will be open for a few more minutes in case someone joins and has a question. Once again, I thank you for tuning in to week 6 of the live sessions for the course Computational Science and Engineering. Uh, this is Sourav Goswami from IIT Bombay, and I look forward to interacting with you next week. Thank you.